Okay, so let us get to lecture 4 on kernel memory optimization that is part of memory management. Now, the kernel is meant to maximize the use of the RAM resource. In fact, all resources, but we are covering RAM resource. So RAM is expensive, it is limited, but the RAM memory can truly increase performance of a system. So the kernel is structured and built to enable that. What we will be covering here is how the kernel does some of that, not individually at a process level, but overall at a system level now. So one of the concepts is the page cache. Now, when you do I/O, typically you will go to the disk and read files, and next time you need it, you will go back to the disk. But what the kernel does is that you have RAM available and you're still going to the disk. So what the kernel will do is move those files and move those blocks and pages over to the RAM so that the next time you come back for the same request, it can serve it from the RAM. So for this purpose, the kernel manages a page cache. Page cache will cache two kinds of things. There's probably the swap built in as well, but the block data I/O reads that are happening, so it will cache those block data reads. So next time you go for the same block data read again, and it'll get you from the page cache. And the other ones are, we discussed a lot of the memory mapped files where you go to the memory and the memory address from behind the scenes is reading the files. So it is going to page cache those memory mapped files behind the scenes for you. Here's an example. So the read request will come. The first read request that'll come assumes you do not have the file in cache. So what you will do is at that point, the kernel will read the data from the file system, but then it will allocate a page frame and copy the data from the file system into that page frame. It will update the cache and tell here, I got this page frame in this location, cached, and then it adds it to an inactive LRU list. And the caches are managed between two lists, the inactive LRU and the active LRU. And the purpose of both of these is to pretty much manage the part where pages come in, but when you need to evict them, keep the knowledge of what are the pages you will take out first. So for that purpose, it's constantly managing between an active cache list and an inactive one. So when you get data for the first time into a cache, it will go into an inactive list. And it will propagate itself to an active list when you read the data again the second time. Overall, the kernel tries to optimize between these as with 2/3 of the data being in the active list and 1/3 being in the inactive list. So regardless if there are elements that move to the active list because they have been reused, but as more elements come in, the bottommost in the active list will actually fall back into the inactive list. So this is what the kernel will do. First time, put it into the cache, and when the second read comes, then read it from the cache. And over time, if things are not being used and you need to reclaim memory, then move out the items that are in the inactive list. Now let us go to writes in a page cache. So we are writing, we intend to do a file write back to the file system. But what happens is we do have the page cached in memory. So we will write to the cache in memory, not immediately to the disk. And the page will get marked dirty. And that page at a later point in time by a kernel write back thread will be picked up because this page is marked dirty. And there are settings, and I think this default setting is about 30 seconds. After 30 seconds, the page will be picked up and will be swept into the write back process so that it is written back into the disk. This saves a lot of writes that may be happening, and you can accumulate a lot of writes into the memory and then write to the disk. So overall, it makes the system efficient. One thing you have to note is when you do that, you are not immediately writing to the disk, which means that if your server were to crash, you are going to lose some data. When you absolutely cannot afford to do this, you actually will use a setting to write back to the disk immediately instead of writing back in an async manner. And you are able to flush your contents by an explicit use of a system call to flush your dirty buffers back to the disk. And that way you ensure that the data is on the disk. But for the most part, you will use writes that actually write to the RAM system, and later on, they go to the disk through a write back process. That was for file backed data. There is another process on swapping, and there is a swap that the kernel allows to be created, a swap space. The swap space is there such that if the kernel has physical RAM memory, and you can look at the swap space as an extension of the physical RAM memory into the disk. Now, the disk can never be as fast as a physical RAM, so the purpose of the swap is to just take out pages that are not being used and move them to the disk such that you have more physical RAM available for processes that are more active in their usage. The kinds of things that you would move into the swap disk are things that do not have a file backing, because pages that did have a file backing, those you can just delete because you can always get them back later. Anonymous memory pages do not have a file backing, and these are going to need to go to the swap space. There are also elements of other memory mappings, and when you have a private memory mapping and you have a dirty page, you're working on it. You don't intend it for it to be saved to the file space ever, but you have made changes that you expect to be in the memory, and those can be moved to the swap space as well. And similarly, dirty pages of IPC shared memory regions, when you are basically sharing memory between processes, and those are dirty as well. So similar model, you don't want to lose that while the server is up and running. When will you use a swap system? You can configure it, and you can configure the amount of swap space you want to use. You can configure the number of partitions you want to use for the swap space, and you can use enable swappiness factors to tell how much of, how aggressive do you want the kernel to be swapping. So here is a swap out process, and assuming you want the kernel goes through its process of reclaiming and determines it wants to swap out memory. So for that purpose, it'll select pages for swap out, and the pages that it will select are from the inactive list in an LRU model, so anonymous inactive. And once it has selected those pages, instead of just pushing them out to the swap area, it puts them into a swap cache first. And the purpose of the cache is to be an interim that during the time when you are moving the page to the disk, it takes time. And during that time, if there is an access to that page, you can actually have it in memory and reverse the action. And so it supports concurrency of you're trying to swap it out, but some process now comes in and wants the page back. So the kernel uses a swap cache as an interim of moving a page out first. Then it will also change the page table settings, and it will make the page present flag as no, it is not present. But in the case of a swap page, it also enables the address of the page on the disk. And that pretty much is a swap area and a page index that it maintains. And so you will be able to tell by looking at the page table entry, the fact that this page is swapped out and that here's the specific address for the swapped out page. So when you are trying to access this page, you will be able to go and get it back from the disk to the memory. So the operation completes with the swap out to the disk. When the CPU is running and these pages are swapped out, they are not in memory anymore, what happens? Well, if the CPU expects a page because the user's code has an address that it is trying to either read or write data to, and it does not find a page table entry, or that it does find a page table entry, but if the operations are not matching up, for example, typically you may want to be writing when you only have a read eligibility, the CPU is going to throw a page fault. And the kernel has the page fault handler. And in the handling process, if the kernel determines that this is actually an invalid access because the program code is trying to access a memory region that is maybe not even assigned to it, or it is trying to write into a read space, and the kernel at that point will say, well, that is an illegal access. It will throw a segment violation fault. The other scenario is that it can be a minor page fault. Now, minor means that the kernel did not have to go to the disk to manage this. And typically in a minor page fault, the kernel will say, okay, you want this page and I did not just allocate it to you, because the kernel does on-demand allocation, and then it will allocate a page frame and then set it up and give it back to the user. So the code can resume from there and move forward. There is also a possibility that it is a scenario of a major page fault. Major page fault simply means I have to go to the disk and get data. It is just going to be slower. With all these changes, once the kernel has the page, it has to make sure that it has updated the page tables, because the CPU is going to use the page tables to know where the physical address for that page is. Let us now consider some page fault scenarios, and one is a page fault of a page that is swapped out. There are a couple of scenarios that play out here. One is that the page is still in the swap cache, which means it is still in memory. And in that case, what the kernel has to do is move the page back out of the swap cache and say, okay, we can use it because there is an access on it now. The other scenario is that it is actually in the disk now and there is no page frame allocated to it. So the kernel is going to allocate a page frame, go to the disk, move the contents out of the swap space in the disk, and copy it into the frame. And then it has to do the page table entry sets to mark the page back as present, and that is available to use, and put the page frame address in that page table entry. And the page also goes back to the anonymous inactive list at this point because it has been accessed now. And the kernel will return back from the page fault handler so that the CPU can resume processing. Another scenario is where there is a major page fault, but the page is a file-backed page. So in this case, you will just get the page back in from the file system. And the kernel at this point will have a similar process. It'll allocate a page frame. It will copy the page contents from the file system into the page frame. It will get it back into the inactive cache list. And it will also then update the page tables with the address of the page frame in the page table and give back the processing to the CPU so the CPU can execute again, and the next time the instruction will pass through because the page is actually available now. There are also a few tools. So from a kernel perspective, you want to know what's going on overall in the system, and you can get the overall memory information by doing a cat on /proc/meminfo. So meminfo is the file that the kernel will keep updating based on how the memory is changing. And on the left side here, what I have is total parameters, like mem total is total amount of physical memory available. Free is the amount that is free. Mem available is actually the amount that is net available, and there is a slight difference. You usually want to go with understanding total memory and looking at the other parameters, because a lot of the memory could be in caches, and the caches can actually be freed up. So just because the memory is not free does not mean that it cannot be freed. So free is absolutely free, and then the differences are that available will mean that in an attempt to reclaim memory, it can get back even more memory. So then the big numbers are the cached number is typically the big number, and this is the page cache where the page file backed caching is happening, the anonymous page caching is happening, the buffers page caching for block IO is happening. So all that is in the cache number, and the buffers number is usually the smaller one, but I think that's where the kernel buffers that are bringing back data from IO, etc., that's used temporarily for that. Swapped cache is the cache on the way to be swapping out to the disk. So we talked about that. Then you look at your total active and inactive cache, and active shows the numbers in active, and inactive are the ones in inactive. And roughly 2/3 of the memory is allocated to active, 1/3 is allocated to inactive. Then this further is divided into the anonymous versus the file distributions. File mapped memory is different. You can delete those, and there's a file backing anonymous. You cannot delete those. And if you have swap, they can be swapped out, but if you have disabled swap, you do not have the ability to swap, then you cannot just move anonymous memory out. Then we have unevictable. In this case, the unevictable and the M-locked are the same. This is just page process memory that cannot be moved out because we have M-locked it, memory locked it to physical memory. Then swap total is the total amount of swap space available. In my case, I have 0 available, so obviously there is no swapping going to happen because it is disabled. Dirty pages are the pages that are dirty but have not been written to the disk yet. The dirty pages will be going through the write back process, and when the write back starts, the dirty count will come down and the write back count will increase, which will inherently show you that the write back is happening. It is just not completed. So the dirty shows you pages that do not have saved data in the disk. They move to write back, and then you know that it's actually being written to the disk. And when both of these are 0, then you know that everything is on the disk. Anonymous pages are again just a sum of the anonymous memory that you're using. Mapped is the amount of the mapped file mapped memory. Shared memory is the memory that is shared between processes. On the right side, there are several kernel memory structures, slab, and I'm not going to cover that, but if you want to get into that, you could also look into the proc/slab info, and that file gives you a lot of information about the kernel's internal data structures and what data structure is using up how much of the memory. Then kernel stack, page tables, these are all the page tables we have talked about for memory management, and it tells you that about 6.7 megabytes is being used for page tables here. They pretty much map the virtual to the physical memory. The other piece that we want to discuss is when these tools tell you that the memory is coming down, what does the kernel do? And the kernel has finally got a decision to make. The system can go out of memory, and at that point, if there is no reclaimable memory left through page caches or through the kernel internal data structures, then the kernel has to decide, okay, so I need to kill a process, because if you kill a process, you can reclaim all the memory from that process. The way that works is the kernel will select a bad process, and it is called a bad process just because it's trying to select the worst process around there such that it can kill it. This is an algorithm, and the kernel gives an OOM score, out of memory score, to every process. The higher the out of memory score, the greater the chances that you are going to be killed by the kernel when there is a problem with memory on the system. The highest score is 1000, which means you will definitely be the one or one of the ones to be killed. And the lowest score is 0, which means we will not kill you. And everything else can be in between. The kernel tries to preserve things that are not causing a problem. One of those methods is if you have been running for a long time, then you are likely not a cause of the problem that the kernel is experiencing now, that it is probably a more recent process that is causing memory issues. So higher CPU time decreases the possibility that the kernel will choose to kill you. Also, small memories do not help the kernel a lot, but larger memory numbers help the kernel. The kernel does not want to kill 100 processes to save memory. Rather, the kernel may kill one process and get memory back to revive the system. So that's another factor It has to be reasonably large. As a user process or in user space, you can also provide an adjustment to a process's score using the OOM_ADJ parameter in the proc PID directory. And you tell the kernel basically, hey, I'm adjusting this one down or up. That way the kernel understands your own choice as running these processes on what you want to be killed and not killed. So the OOM killer does come in, and that's how the OOM killer operates. The algorithm is more complicated, but these are some factors that the OOM killer will use. There are also other tunable virtual memory settings. Now you can read about these yourself, and I'm not going to go through all of these. They are interesting, and you can read about them, and you can search the web and just find out if there are some tunables that you want to play around with. Things that I have found reasonable to learn and understand are these dirty ratios. When does write back happen actually? The swappiness, whether you have swapping enabled, disabled, or how aggressive should the kernel be when it comes to swapping behavior. And so I think some of these are reasonably useful to go and learn about. That is it on the kernel memory optimization, how the kernel tries to operate and provide maximum use of memory for the processes that are running in there. The next lecture will be on memory control groups, and that will be the last one on the topic of memory. Okay, all right, thank you.